Induction motor. Induction motor consists of the stator with a three-phase winding and the rotor. The rotor rotates, and our task is to calculate the torque as a function of the rotation speed. First, let me explain the physics. The stator winding generates the rotating magnetic field, and this rotating magnetic field induces eddy currents in the rotor bars. You know that eddy currents always resist the magnetic field that induced them, so there is an interaction between the magnetic field of the stator and the eddy currents in the rotor, resulting in the torque. Now let's consider our options. When the rotor is motionless, the speed is zero. The stator magnetic field generates currents and there is a torque. We can model this very simple. Draw motionless stator, motionless rotor, specify currents and calculate the torque. Another option, when the rotor rotates with a synchronous speed. In this case, there is no torque because rotor and the magnetic field of the stator go side by side. There is no eddy currents in the rotor. And we can model this by specifying zero conductivity in the rotor bars. We will have motionless rotor with the zero conductivity rotor bars. Now please take a look at this table. Motionless rotor, normal conductivity, synchronous speed, zero conductivity. And in between, for some non-zero rotating speed, we should attenuate the conductivity value. Now please take a look at this page in Wikipedia. You see this is the equivalent circuit of the induction motor. And here is the rotor resistance divided by the slip. We will utilize the same approach. Okay. Now let's start QuickField. In QuickField, I create new problem. Motor AC. Next. Problem type is AC magnetics. Frequency is 50 Hz. Every simulated device is a three-dimensional object. I'm going to simulate only a single cross-section of the induction motor, so the model class is plane parallel two-dimensional. And the motor axle length is 50 millimeters. So I'm going to change the length units to millimeters. 50. You see the product includes the geometry model file and the data file. And I am going to use the electric circuit to specify the connection between the slot conductors. So I will type in the circuit file name here. Finish. On the left is the problem tree, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. Here is the file, and I will import the model. Here is the model. You can recognize here the stator, the rotor. Let's assign labels. To labels, we will be able to distinguish one geometric object from another. Click the object to select. Make sure you are in Select Objects mode. And then type in the label name here. This is rotor. Click here. This is shaft. Click here. This is stator. Now let's zoom in. Switch the zooming mode off. I'm going to assign label to the rotor bars. Click to select and type in the label name bar. In fact, you can select multiple objects at the same time. Just hold the Ctrl button pressed. And there is even more faster way. You see the motor features rotational symmetry. There are 36 bars. I'm going to assign label to the bar and then duplicate this bar. Right click, duplicate selection, rotation 10 degrees, and I need 35 copies more. Okay. Now you see all bars are labeled. In a similar way, I'm going to assign label to the wedge. Click here, type in the label name, wedge. There are 48 slots in the stator, so I'm going to duplicate the wedge and rotate it by 7.5 degrees, and I need 47 copies more. Right click, duplicate selection, 7.5, 47 copies more. Okay. Next, let's assign label to the air block. Between the stator and rotor there is an air. Zoom in, switch the zooming mode off, click here, hold the Ctrl button pressed and click here to select another block. These blocks are air. Next, I have to assign labels to the slot's internals. Most space is occupied by the insulation. Click to select, assign label insulation. And there is the insulation between the conductors. And I have to assign labels to the conductors. The fast way to assign labels would be to select the entire half slot, right click and drag. This would be the insulation. And then I will assign labels to the conductors. Click to select and hold the Ctrl button pressed to select multiple objects at the same time. Or again, you can use the rubber band to select a group of objects. Right click and drag. Hold the Ctrl button pressed and again right click and drag. These are conductors phase A+. And the similar way I should assign proper labels to the conductors in other slots. It takes time, so I better skip this section. Okay, I have assigned labels to the stator slot internals. Here you can see conductors of the phase A+. Then follows the conductors of the phase C-. Then follows the conductors of phase B+, and so on. If you click in a free space and check statistics, you will see that all blocks are labeled. Next, I'm going to assign labels to the boundaries. It is considered that the magnetic field is contained within the stator, so there is no magnetic field outside. And for the external boundary, I will assign label external. External. And I'm going to assign label to the middle line in the air gap. Zoom in, switch the zooming mode off, click to select, and you see the circle consists of two arcs. I have selected one half. Now hold the Ctrl button pressed and click to select another half. Again, I will zoom to fit to make sure that the entire circumference is selected. This is the air gap middle line. Air gap. So far, these are just text labels. Now let's provide physical properties for the labels. Double-click the label name in the tree and type in the relative permeability of the air, which is 1. Okay. And relative permeability of the insulation is 1. Okay. Shaft is made of stainless steel, so the magnetic permeability is 1. The rotor steel permeability is 1000. The rotor is laminated, so there is no eddy currents in the rotor. I do not specify electrical conductivity here, so QuickField will not calculate eddy currents. Okay, the same steel is used to make stator. Magnetic permeability 1000. Okay. Rotor bars are made of aluminum with the magnetic permeability of 1 and electrical conductivity at the anticipated temperature of 70 degrees Celsius is 31.1 megasiemens per meter. And these conductors are connected in parallel. Okay. Now the wedge is made of dielectric material with the magnetic permeability of 1. Okay. Now let's assign properties to the phase conductors. Magnetic permeability of copper is 1. The winding temperature is 70 degrees Celsius, and at this temperature the copper electric conductivity is 46.8 megasiemens per meter. Conductors are connected in series. We'll copy this value. The same material properties I will assign for other phase labels. Same magnetic permeability, same electrical conductivity, and conductors are connected in series. Phase B minus, phase B plus, phase C minus, phase C plus. Now I should provide physical properties for the edge labels. Magnetic field doesn't leave the stator, so here at this boundary I specify 0 magnetic potential. Okay. For the air gap, I do not specify any data. I use this label only as a label to quickly find the middle line in the air gap. Okay. The 0 mark indicates that this label doesn't have any data. Okay, now let's open the electric circuit file. Here it is. We should place all conducting blocks in the circuit. These are phase conductors, and the rotor bars. Rotor bars terminals I leave open. There is no electric circuit connected to the rotor. I already have specified that bars are connected in parallel, and that is enough. Phase conductors are connected to make phase coils. I should connect conductors ending. So I will rotate these blocks here. And connect the endings with the wire. This way I have constructed the phase coils. The coils are connected in star, so I add the wire here, and the coils are connected to the three-phase voltage source. I will add the voltage source here, and here, and here. And connect the voltage source to the winding with the wire. Okay, now let's correct the labels. Double click. This is voltage source phase A, and the magnitude is 220 multiplied by the square root of 2, because in QuickField we should specify the magnitude. I will copy this value. Phase 0. For the phase B, V underscore B, the same magnitude of the voltage, but the phase shift is 120 degrees. And for the phase C, the same magnitude of the voltage, but the phase shift is 240 degrees. Okay. And here I should switch back to presentation. You see the conductor's length in the slot is 50 millimeters. That is the axle length of the motor. But there are out of slot conductors connecting, for example, slot A plus number 1 and A minus number 13. These conductors are called overhang, and there is conductor on the front side and on the back side. These conductors add up to the phase coil resistance. These conductors are not present in the geometry model, so we have to include them in the electric circuit. You can find the calculation details on the example web page. Here I will present you with the result. The overhang resistance is 50 ohms per each phase. So here, back in QuickField in electric circuit, I will add the resistors. Here, and here, and here. Now let's again correct the labels. This is overhang A, and the resistor value is 15 ohms. This is overhang B, 15 ohms, and this is the overhang C, 15 ohms. Okay. Now the circuit is ready. Before running the analysis, I should build the finite element mesh in the geometry model. Just press this button. Now save all problem files and solve the problem. Okay, the problem has been solved. Let's take a look at the results. Here you can see the column map of the current density, root mean square value, and the magnetic field lines. The field lines are displayed at some fixed moment of time. Remember, the currents are alternating, so let's change the moment of time and make sure that the magnetic field is indeed rotating. I will adjust the field picture and switch off the color map of the current density. Then I'm going to change the time. In AC magnetics problems, it is called the phase. Now the phase is 0. I will switch to 5 degrees. Okay, I'm going to change it a bit faster to create a moving picture. Well, indeed, the field picture is rotating. And the rotor is motionless. There are current induced in the rotor bars. I can use the contour tool, click to select the bar, follow to the integrals. This is the cross-section area of the rotor bar, and this is the total current. So there is the current, there is the running magnetic wave, and the current interacts with the running magnetic wave, and the result is the force. So I can calculate the force here. And if I select all conductors, I can calculate the torque. I can click to select blocks one by one, or I can build the contour in the A gap. Contour, clear, zoom in, switch the zooming mode off, click here to select and click here to select. Now let's zoom to fit. The contour is constructed in the A gap, and if I change the contour direction to become the counterclockwise directed, I will select the contour internals. Now I can calculate the torque. The average value 6.2. Let's remember this value. Copy, and I will paste it here. This is the stall torque. The rotor is motionless. Let's find the current. You can find the current if you take a look at the circuit results. Let's measure the current in the phase A. So this is the current magnitude and the phase shift. You see we have the inductive loading. So the current lags the voltage. Again, I will copy this value. This is the current magnitude and the current phase shift. You can calculate the cosine function of this angle and find the power factor. You can multiply the current by the voltage and find the power on terminals. And the output power is 0 because rotor is motionless. Now remember that we can attenuate the rotor bar's conductivity to simulate non-zero rotational speed. I could do it manually. Open the label properties, specify some other value of the electrical conductivity, solve the problem again, build the integration contour to find the torque, open the circuit, calculate the current, but there is a way to automate repetitive tasks with LabelMover. First, I should select the base problem, which is our problem motor AC. Then I should specify the values to measure. I'm going to measure the torque. Again, I will use the A gap label to construct the integration contour. And here I will choose Maxwell torque. Average. Add. Well, that was easy. Perhaps I will measure some other values as well. I will measure the losses in the rotor bars. select the label in the tree, and select the integrals. Joule heat average value. And I'm going to measure the current in the circuit. Select the phase A, current magnitude, and the current phase shift. We have a symmetrical phase system, so there is no need to measure the current in other phases. They will have the same magnitude, only shifted by the 120 degrees. Okay. So that's all the values I need. Next, I should specify steps. What should be changed in our problem setup? Record steps. There are two step types. You can change properties and you can move some object in the geometry model. I'm going to change the properties. I would like to attenuate the bar conductivity. Conductivity. Now the conductivity is 31 megasiemens per meter. I'm going to increase by percent and specify, for example, minus 20%. Add step. You see, new problem is generated. This problem features the same geometry model file and the same electric circuit file, but the data file is unique, and in this file the bar conductivity now is 20% smaller. Okay. I would like to repeat this step. Close, edit. I will repeat this step 10 times. Okay. Now that's all. We have the base problem, we have specified the values to measure, and we have specified the steps to perform. Click Get Results button. A set of problems is generated. All problems are based on the same geometry model and the same electric circuit file, only the data file is unique. Then the problems will be solved and the results, the Maxwell torque, the Joule heat, and the current will be stored here in the table. Now you may note that several problems are opened and simulated in parallel. That's because on my computer there are several cores in the processor. And if I open the task manager, you will see that QuickField applies almost all powers of my multi-core processor. This way you can get results much faster than solving problems one by one. But if the resources of your computer are limited and you, for example, do not have enough memory to run all problems in parallel, you can follow to the Tools options and disable the multithreading in LabelMover. Now the results are ready. Each line corresponds to the specific rotation speed, to specific rotor bar conductivity. You can take a look at the plot. This is the Maxwell torque. This is the stall, where the rotor speed is 0, initial value of the electrical conductivity of the rotor bar. Then the speed increases. This is the maximum torque, and then the torque falls down. If we will continue to reduce the electrical conductivity, we will get the 0 torque that corresponds to the synchronous rotation speed. You can copy all the results to Excel, select all the values and copy. And here you can post-process the results. Torque, current magnitude, current phase shift, and the joule heat. If you search for the induction motor on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results can be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.